Section 2.9 in Lay's textbook, it's about change of basis. Given a basis, here's how the definition goes. Given a basis for a subspace A, S, for each vector x in S, the coordinates of x relative to the basis B, these are the coordinates of x, we can write what? Uh, a vector in S as a linear combination of the what? Vectors in our basis. So the constants C1, C2, C3, all the way to Ck are called the coordinates of vector x relative to the basis B. This is the notation, so you read this as coordinate vectors of x relative to basis B. That's the notation. Sometimes we read that as B coordinates vector of x. So either way, it's okay. Sometimes people read it this way, some other time people read it the other way. This topic is also known as I mentioned, change of basis. Here's an example maybe that will clear the definition. Determine the components of the vector v, which is 1 comma 7, relative to the order bases 1 and 2 and 3 and 1. In other words, the vectors in our basis happens to be these two, and we can tell they are what? Non-collinear because they are not parallel to each other, and they are linearly independent, and they span R2. So therefore, they do form a basis for R2. However, we need to find C1, C2 such that we can write this vector as a linear combination of these two vectors in the basis of R2. So we go 1 comma 7 is equal to what? C1 times B1 plus C2 times B2. And lo and behold, we get this system of non-homogeneous linear equation, which has a what? Unique solution, namely 4 and what? -1. So therefore, the vector v, which happens to be 1 comma 7, can be written as linear combination of the what? Vectors in the basis of R2 as follow. We need to take 4 of these guys minus 1 of these guys in order to get what? The vector v. In other words, we have to what? To get, what was it? 1 comma 7. We need 4 times 1, 2, and minus 1 times 3, 1. There you go. So the coefficients C1 and C2 are called what? Components of the vector v relative to the base B. And here's the notation. So we go components of vector v relative to base B is 4 comma -1. So what does that mean geometrically? Geometrically means if you have a vector in R2, you know, these are called standard bases. Remember, this guy was the I vector, this is like J vector, which are unit vectors in positive X and Y axis. So in order to express what? V relative to the standard basis, well, that's easy because you take one of these guys and 7 of these guys, and lo and behold, you're there. Geometrically, that means if this is I and that's J, if I take 1I but 7J, remember this is J, so I take 7J here, and then find the resulting vector by forming this parallelogram, I would be at 1, 7, which that's where I want it to be. So you take one of these, 7 of those, you be at 1 comma 7. However, if the bases change and you are in non-standard bases, notice this is no longer 1, 0, 0, 1, it's 1, 2, and 3, 1. So how many of these plus how many of those takes you still to what? Vector v, which is 1 comma 7. Well, turns out we already did that. So if this is B1, which is what? 1 comma 2, and this is B2, which is what? 3 comma 1. We're supposed to take 4 times B1 and negative 1 times B2 to get to 1 comma 7, which is the same destination as we had in case 1. So what you do, if this is B2, because you need negative B2, so you go opposite direction. And this guy right here is B1, right here. Take what? 4 times of B1. And now form this what? Parallelogram and connect the diagonal. And lo and behold, you'll be at 1 comma 7. So geometrically, the question is, instead of getting to 1 comma 7 via I and j, how would you get to the same location via what? These vectors in the basis of R2, which happens to be non-standard. They are no longer I and j. So it turns out we have to take 4 of these and negative 1 of those to get to 1 comma 7. Here's an easy way to get find the components of the vector v relative to non-standard bases 1 and 2. What you do, you make this augmented matrix, list the vector b1 in column 1, between the column 2, and the vector v as your constants. Put this in row echelon form. Remember, you're trying to solve for C1, C2, and lo and behold, the answer would be C1 is 4, C2 is negative 1. So therefore, vector v can be written as linear combination of what? B1 and B2, correct? And you have to take 4 of these minus 1 of these in order to get to the destination, which is 1 comma 7. You can also do the same thing for polynomials. It doesn't have to be vectors. In other words, let's say you are dealing vector space is P2, which is all polynomials of degree 2 or less. Determine the components vector of P of x, which is 5 plus 7x minus 3x squared, relative to first standard ordered basis, which happens to be 1x squared. So this is your P1, P2, P3. And then ordered basis, what? P1, P2, P3. So these are standards. These are non-standards. Any polynomial of degree 2 or less can be written as linear combination of these guys. So these guys span P2, and they are linearly independent, so therefore they form a basis. So the notation goes, the components of P of x relative to B is, because remember we're trying to construct this using these 3 vectors. So you kind of go, okay, I need 5 times P1, 7 times P2, and I need negative 3 times P3 to get to my answer. In other words, I need 5 of these plus 7 of those, negative 3 of those to get this. Therefore, the components of polynomial P of x relative to standard basis B is 5, 7, negative 3. Sometimes they use brackets. I don't think that's a major issue, but just in case. So these are called components of P of x relative to the standard basis B. Notice components are the constants, okay? But on the other hand, the components of P of x relative to these this basis, which happens to be non-standard. So there are 2 ways to do this. First, what you do is form this linear combination and set it equal to P of x. In other words, this would be the same as C1 P1, C2 P2, C3 P3 is equal to P of x. When you form this linear combination on the left side and set it equal to P of x, The result is a non-homogeneous system of equation, which you have three unknowns, three equations. And when you solve this, you get a unique solution, and the answer would be C1 is 40, C2 is -10, and C3 is -3. Therefore, what that means is your polynomial, which was 5 plus 7x minus 3x squared, can be written as 40 times P1 minus 10 times P2 and minus 3 times P3, and that will give you your polynomial. So these are called components of what? Polynomial P of x relative to the what? These vectors in the basis of P2. So that's one way to do it. The other way, which is a tiny bit easier, is by forming this augmented matrix. Okay, so what you do in the first column, put the coefficients of x squared, x, and constant, okay, in order. So notice P1 is 1 plus 1x plus 0x squared. So I have 0 for x squared, 1 for x, and 1 for constant. So I'm just picking up the coefficients. For P2, this is 2 plus 3 times x plus 0x squared. So the coefficients of P2 are 0 for x squared, 3 for x, and 2 for the constants. P3 is what? 5 plus 1 x plus 1 x squared. So the coefficient of P3 happens to be 1, 1, 5. Okay? And then you augment that with P of x, put this in row echelon form. Remember, you're trying to solve for C1, C2, C3. Therefore, the answer comes up as a unique solution, which is 40, -10, -3. So C1 is 40, C2 is -10, C3 is what? -3. Excuse me. So what does that mean? Then again, it means you can rewrite P of x as 40 times P1 minus 10 times P2 and minus 3 times P3. So this is called change of basis. Sometimes it's easier when you convert the basis from one form to the, when you convert or express the, vector in terms of a different basis. It just makes the job easier. And, there are a lot of applications regarding change of basis, depending whether you use in engineering or some other fields like computer science and so on and so forth. Thank you.